All right. So a quadratic function is a function of degree 2. We talked a little bit about this yesterday, and it can be written in something called standard form. And standard form looks like this. It can be written in a variety of forms. And in fact, that's why we talked a little bit about factoring yesterday, right? Because when we have a polynomial expression, we can expand it, we can factor it, we can play around with a polynomial expression, okay? And express it in different ways, okay? Same thing goes for polynomial, or for a quadratic function. Quadratic function is a type of polynomial function, okay? So quadratic function of degree 2, it can be written this way. Y equals ax squared plus bx plus c, where a is not equal to 0. Okay, and this is called standard form. So standard form is sort of where everything's expanded out. There's no brackets. All like terms have been collected. And every quadratic function will take this form. Okay? The only condition is that the value of a can't be 0, because if a was 0, then again, the x squared term would disappear. Then we just have a linear function. Okay? Now, the values of a, b, and c are going to tell us what the graph looks like. Okay? So the thing that's going to make one quadratic function look different from another are the values of a, b, and c. Just like in a linear function, what differentiates one from another is the values of the slope and the y-intercept. Okay? So the graph of a quadratic function is called a parabola. Parabolas look like this, or they can look like this. Okay, so same shape, but they can kind of open upwards or open downwards. Okay, so again, I mentioned this, but the values of a, b, and c determine where the parabola is on the Cartesian plane. Okay, so where does it appear on the xy plane? They determine, does it open upwards? Does it open downwards? And they also determine how wide is it, right? Is it a really sort of narrow parabola, or is it a really, really sort of wide parabola? Okay? This point over here is called the vertex of the parabola. Okay? And the vertex of every quadratic function is either the maximum value of the function or the minimum value of the function, right? Because if you think about it, if this is the function, the first one, this is the bottom of the function. This is the lowest it'll go. So in this case, this would be a minimum. In this case, this would be a maximum. Okay? So this is a min. This is a max. Okay, these functions are symmetrical, and they're symmetrical about a vertical line, and that vertical line is called the axis of symmetry. Okay, and that axis of symmetry is going to pass through the vertex. And, you know, that's kind of, you can kind of see that, how that works. Okay, so the axis of symmetry, I'll just draw one of them, but here's the vertex. Right, this is the axis of symmetry. Okay, intercepts. So intercepts are where the graph hits the x-axis and the y-axis. Okay, so if I now put in a Cartesian plane, okay, now if you think in terms of domain and range, right, and I stick one of these in here, okay, there's an arrow that goes to the right infinitely, right? This arrow, although it's also going upwards, the horizontal direction is going right. And this horizontal direction is going to the left. And so the domain of these things, unless there's a context, is always going to be x as an element of the real numbers, okay? So what that means is that there's always going to be a y-intercept, because it's always going to pass through the y-axis. If the domain is everything, the y-axis is when x equals 0, it'll always have a y-intercept, okay? Not necessarily true, though, of the x-intercepts, because remember, it's got a lowest point and a highest point, or a highest point, depending on the way that it opens, okay? So the one that I just drew has an x-intercept and a y-intercept rather, and 2 x-intercepts, okay? But you can also have a scenario where a parabola or a quadratic function has a y-intercept but no x-intercepts. So if I drew something like this, okay, well, the highest point is below the x-axis. So this is never going to hit the x-axis. Okay, so this will not have any x-intercepts. It will have a y-intercept, though, because at some point this arrow will continue to the left and pass through the y-axis. Okay? It can also have 1 x-intercept, and that would look like this, where the vertex is actually lying on the x-axis, like this. Okay, so this is 0 x-intercepts. This one is 1 x-intercepts. And this one is 2 x-intercepts. Okay, so these are some properties of these functions and their graphs. Okay. What we're going to look at today, so I'm going to go backtrack in our notes a little bit, is specifically the vertex form of the equation. And when we write an equation in vertex form, as you might guess, it's going to give us some information about where the vertex is on the Cartesian plane, right? So that vertex is like this point right here. Where is that point? And that, since it's a maximum value of a function or a minimum value of the function, when we're in a context, can be pretty important information, right? These functions often model maximum height. Well, we might want to know maximum height or maximum revenue, okay? That's pretty important. All right, so let's go backwards. Are you okay with me going backwards for now? Okay. Okay, so written in vertex form, a quadratic function looks like this. Okay? Y equals A times x minus p in brackets squared plus q. For today and tomorrow, we're not really going to worry so much about how do we get something into vertex form, how do we switch from one form to another. but we will do that later on this week. Okay? A, P, and Q are numbers. Okay? The only condition here is that, again, A cannot equal 0, because if A was 0, this entire bracket would go away, and then you just have y equals q, y equals a number, which would be a horizontal line. Then you don't have a parabola anymore. Okay? So what we're going to do to figure out what these parameters mean, right? These three values, A, P, and Q, are each a parameter that are going to affect the graph, is we're going to examine them one at a time. Okay? So the first thing we're going to examine is this guy Q. What does Q do? Okay, so I want to look at the graph y equals x squared. And this is kind of going to be our control. You know, in like science experiments, you use a control. So as we examine each parameter, we're going to use this y equals x squared graph as a control. Okay, so what I'd actually like to do is to make a table of values to graph that, because when you're going through this for the first time, it's really important to get a sense of how these variables x and y interact with one another in a quadratic function, okay? So I'm going to try and be fancy here and pull up some grid paper. I should have paper backgrounds. Ah, there we go. Let's pull that one up there. And I want to make this guy smaller. No, I don't want to do that. Wait, I got to go to the mouse. Not that, this. Okay. Okay, now you guys, would it be actually more helpful for you if I didn't use graph paper so that you guys can kind of just wing it the same that I would? Is that better? Okay, let's do that. I don't want to bother with this stuff. It's like too finicky. And to be honest, I never use it when I'm working stuff out. So let's just not do that. Okay. Graph the following. Y equals x squared, y equals x squared plus 3, and y equals x squared minus 5. So we're just going to graph y equals x squared by hand, and then we'll use a technology to look at the other two and to see what happens and how they compare. Okay? So let's look at a table of values. And let's just do that for y equals x squared. Ooh. Okay, so let's look at -2, -1, 0, 1, and 2. Okay, so if y equals x squared, if x is -2, what's -2 squared? -2 squared is what? Yes. -1 squared is 1. 0 squared? 0. 1 squared? 2 squared? 4. Okay, so if we graph this, Okay, so here's 0, 0. 1, 1. Negative 1, negative 1. 2, 4. So 2, 4 is going to be about here. And 2, 4. And keep in mind, by the way, what about if x was 3? What would y be? 3 squared. 9. What if x was negative 3? 9, yeah. So 3 would be like 9 up here. Okay, so these guys, that's why you get this parabolic shape. Ah, that's really bad. You know what? I'm really bad at doing this when I try and do it from the side. I have to stand straight on. That's my problem. Okay. Because they should be symmetrical. And the reason why we have this symmetry is because when you square something, you get a positive value, right? So the negative x value squared is going to be the same as the positive x value squared. Okay. All right, so that's the basic y equals x squared graph. This is going to be like our control. Okay. Now I'm going to pull up a graphing calculator. How many of you guys have a Casio graphing calculator? Couple. Okay. So I have the emulator here as well. So I will go back and forth and use both. So you guys should do this along with me. Let me actually look for my Casio. There it is. I'll bring up both. Oh, I haven't activated my license on this one. You know what? I can't use my Casio today because I have to go and look up what my license number is. I need to cancel, but I'll make sure. Ugh. Oh, what's it doing? Okay, well, let's just do this for now. I'll make sure to have that ready for tomorrow so I can model for you, okay? But for today, I'll just come around and make sure that you guys are okay, okay? Okay, so what we're going to do is we're going to graph in y1 x squared. Okay, and then the other ones that we're comparing to, oh, now it's working. Oh, okay, maybe I can use both. y2, what were the other ones? Was it x squared minus 3 and x squared plus 5? Oh, plus 3 minus 5. Okay, so x squared plus 3 and x squared minus 5. Okay. Now, when you are thinking about graphing, one thing that you need to consider are your window settings. Okay. When you don't know what the context is, for something like this, I tend to use the zoom standard setting, which sets your window from -10 to 10 for x and -10 to 10 for y. Okay, so if you go to zoom, which is this button up here, there are a bunch of built-in settings. And so I use this one, which is number 6. Okay, so there's the first one, there's the second one, there's the third one. Okay. All right. So let's draw those in our notes. Oh, that's not what I want. Oh, it's here. It's notebook. There we go. Okay. So when it was x squared plus 3, this guy, by the way, is this guy looks like this. And x squared minus 5 looks like this. Okay, so this y-intercept is 0, 3, or 5, and 5. And not necessarily the y-intercept, but the y value of the vertex. Okay, so what do you think q does? The value of q. What does q determine? Yeah. The minimum, yes, okay. Okay, so let's talk more about, can we generalize in terms of specifically instead of talking about the vertex, instead of talking about the minimum, talk about the vertex. Yeah.
The lower the q value is, the lower the vertex is down on the y.
Okay, so the lower the q value, the lower the vertex. That's true. Yep.
Should we talk about point of intersection?
Well, we'll get that. We can make a prediction about the point of intersection, but we'll see if that actually comes true. Okay. What happened to the graph, though? Compare y equals x squared to y equals x squared plus 3. What happened to the graph? Don't think too hard. Like, think as if you're a young kid. How would you describe what happened? What happened to it? Yeah. It got bigger? Where's the calculator? Maybe what I'll do is I'm going to make my window settings a little bit bigger. I'm going to make this like 20 so we can actually see what happens as they get bigger. What happens to the parabolas? This guy's here. Compare the blue one to the red one. Farther down by how much? So this one's at 0. Then this one goes up. How much does it go up by? It goes up by 3. Yeah. This one's at 0. This one goes down. How much does it go down by? 5. Yes. So the q value moves the vertex up or down. And it moves the vertex specifically up or down by the q value. Okay? It's as simple as that. Okay? The q value determines the vertical position of the vertex. Okay, so for example, if q equals -5, the vertex moves down 5 units. Okay? If q equals 3, the vertex moves up 3 units. Okay? All right. Let's look at these ones. Graph y equals x squared, and y equals x squared plus 3 in brackets, and y equals x squared minus 5 in brackets. Okay? So we've already graphed y equals x squared plus 3, or y equals x squared by hand. So let's just do this on a graphing calculator. Maybe what I'll do this time is I'll do it on the Casio. So if you're graphing on a Casio, what you want to do is go to the menu and go down to Graph. And then you can enter each function in here. So I'm going to enter in x squared. Enter. And then in brackets, what was it? I keep forgetting. X plus 3 squared. X, oh, whoops. Nope, delete. X plus 3 squared. And then the next one is going to be in brackets, x minus 5 squared. Okay, and then what you can do is hit F6 for draw. And the nice thing with Casios is that it tends to set the window for you. And there you go. Okay, so unfortunately my screen with the Casio doesn't make it really big over here on the emulator. But you guys can kind of see what happens. So here is the y equals x squared graph. That's the blue one. The red one is y equals x squared, or sorry, x plus 3 all squared. And the green one is y equals x minus 5 all squared. Okay, so firstly, let's just talk in a general sense. What does the p-value do to the vertex? Yeah.
It determines the horizontal position of it.
Yeah, moves it side to side. Yeah? Okay. Moves it side to side. So when we had y equals x plus 3 squared, what direction did the vertex go? Yeah, went left. That's right. Went to minus 3. And when we had y equals x minus 5 all squared, it went to the right, 5 units. Okay? So yes, that's true. Where are we? Here we are. Notebook. Okay, so we can just draw this quickly. Here is y equals x squared. Okay. This right here is negative 3. This is y equals x plus 3 squared. And this over here is 5. And this one is y equals x minus 5 squared. Okay, yeah, so P determines the horizontal position of the vertex. Okay, what you have to keep in mind though is that when you have x plus 3, it moves left. When you have x minus 3, it moves right. Okay, so there we go. question so far? Yep. Oh, yeah. Ha, thank you. 5. It did move right 5 units. That's correct. Okay. All right. So now what we're going to do is look at the A value. So we're going to graph the following: y equals x squared, y equals 4x squared, and y equals a quarter x squared. And I think this one is worth doing a table of values. Okay, I'd like to do a table of values here and just look at what happens. Okay, so what we're going to do, let's maybe do the table of values here. Let's look at x squared, 4x squared, and a quarter x squared. Okay, so let's use these same values that we used before: -2, -1, 0, 1, and 2. Okay, so we should know the values for x squared already. What's -2 squared? 4. -1 squared? 1. 0 squared? 1 squared? 2 squared? 4. Okay? Now, the column to the right, we already know what x squared is. Now we want to know what 4x squared is. Okay, so x squared is 4. What's 4x squared? 16. Yeah, we're just going to multiply these values by 4. X squared is 1. What's 4x squared? 4. X squared is 0. What's 4x squared? 0, yeah. Oh, sorry, this should be 4. Okay. All right, and finally, a quarter x squared. So if x squared is 4, what's a quarter x squared? 1. If x squared is 1, what's a quarter x squared? 0.25 or a quarter. Okay. If x squared is 0, quarter x squared is 0, right? And then these guys, they're symmetrical. So this is a quarter, this is 1. Okay, now if we graph these, it's tricky to graph these all on the same graph because the scale is going to be a little crazy, but that's okay. So let's put maybe 8 here and 16 here. This will be 4, 12, 1. Okay, so I'm going to start by graphing y equals x squared. Okay, so y equals x squared when x is -2, y is 4. When x is 1, or -1 rather, y is 1. When x is 0, y is 0, 1, 4. Okay, so I know my smartboard sucks because it's got all these like dots on it, so it's really hard to see. You know what? Would it be easier if I switched colors? Because I'm using black right now, and all the dots on my smartboard are black. I'm going to do that. Let's switch to green. Let's make sure that the thickness stays the same though. Yeah, it didn't. Okay. Okay, so for 4x squared, when x is -2, y is 16. When x is -1, y is 4. When x is 0, y is 0. When x is 1, y is 4. And when x is 2, y is 16. Okay, so this guy looks like this. Okay? And then I'll switch again to red. Okay? When, for a quarter x squared, when x is -2, y is 1. When x is -1, y is a quarter. Then we've got the 0, 0 point, a quarter, and 1. So this guy looks like this. Okay? All right, so what does the value of a determine? What do you think? Yeah. Yeah, so you can think of it as kind of the equivalent of slope, but slope refers to like a rise over a run, comparing the change in y over to the change in x. Okay, so do you have, sorry, I can't remember your name.
Thomas.
Okay, Thomas. How would you describe it?
I would describe it.
Same way? Okay. So the way that I describe it is sort of how wide or how narrow is the parabola. That's kind of how I describe it. Okay, so what does the a value determine? How wide or narrow? Uh-oh. The parabola is. Okay, and then the last thing that we're going to compare is y equals x squared to y equals -x squared. And I think for this one, I'm just going to do it quickly on the calculator. So let's go to y equals, and I'll just clear these. And we'll put in a -x squared and graph these. So there's one, there's the other. Okay, so what happens when I make a negative? Flips, yeah. So we call that for a parabola the direction of the opening. Okay? The direction of the opening changes from up to down. Okay? So if we graph that quickly, here's y equals x squared. Here's y equals -x squared. Okay, what does the sign of a determine? The direction of opening. Right? So if a is greater than 0, opens up. And if a is less than 0, it opens down. Okay. Now we're going to put this all together. So let's sketch this, and then we will determine all of these different properties. And we're going to try and sketch this without using technology. Okay. So what we want to do when we're sketching this is consider a few things, okay? So what I like to do is I like to look at what are the values of A, P, and Q, okay? Because I know P and Q tells me where the vertex is. A tells me two things. Number one, does it open up or down? Number two, how wide or narrow is it compared to y equals x squared? Okay? So especially when I'm graphing by hand, Okay? So if I have this, y equals a times x minus p squared plus q. Okay? Couple things that I know. The vertex is at, remember that if it's minus p, it moves in the opposite direction. So if it's a minus p, the vertex would be at p. Okay? Q. A tells me direction of opening and wide, narrow compared to x squared. Or compared to y equals x squared, I should say. Okay, so in this case, what do we know for this particular function? Yeah.
We know that the p is negative
Yeah. Yep. So p is negative, so it's negative 5. So, and q is? Negative 4. Okay, so can we tell what the vertex is going to be? Could we tell where the vertex is? How far down or up are we going to move the vertex, and how far right or left are we going to move the vertex? Yeah. Yes, because this is negative, we're going to move it to the right 5, and then we move it down 4. Okay, so right 5, down 4 is the coordinate point 5, negative 4. So we can fill this in right away. Okay, what's the a value? 1. Okay, so what that means is it opens up, and it looks identical to y equals x squared, but it's just been translated. It's been moved from the origin to somewhere else. Okay, so if we were to graph this, 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay. Here's our point. This is the point 5, negative 4. Okay. The a value is positive. What direction is it going to open? Up. So direction of opening is up. Okay. It's going to look identical to y equals x squared. So a really handy thing to do is either to memorize, or I just kind of always jot this down, this little table of values. Whoops. 4, 1, 0, 1, 4. Okay, if it looks identical to that, what we can do is pretend that this is now the origin and plot those points. So if this is now 0, 0, because now we've taken care of the translation of the vertex. Okay, this is like the 0, 0 point. Now we got to plot the other points. So the other points, because the shape of the graph is identical, are going to fall in line with this. So for example, if we go 1 left of that point, the y coordinate would be 1 up. Okay, so 1 left would be here, 1 up. There's going to be a point right there. I got to do this in a different color. This is crazy. My smartboard is not very good, okay? So here's a point that goes right there, okay? If I go to left of the origin, of our new origin, I should say, of our vertex, right? Then I've got to go 4 up. So 1, 2. I've got to go up 1, 2, 3, 4. Does that make sense? Okay. And then on this side, if I go 1 right, I should keep writing some more lines here. I've got to go 1 up. I should mention, guys, if I ask you to do this on an assessment, I will give you graph paper. I'm not going to get you to draw your own grid. Okay? So this, as a sketch, looks like this. Does that make sense? Okay, now axis of symmetry. The axis of symmetry is the vertical line about which the graph is symmetrical. So if we were to draw that in, it would be the line, the vertical line that the vertex goes through. Okay, now how do we actually write that out in terms of an equation? Well, this happens to be the line x equals 5. Everywhere along this line, doesn't matter what the y value is, x is equal to 5. Okay, so this is the axis of symmetry. Okay, what's the domain? Yep. Okay, so a domain of a function is the set of all x values for which the function, it makes sense. What are the input values that we can put into this function? Okay, and then the range are the y values. What could we get out once we put in these input values? Okay, what is the domain of this function? Yeah. Yeah, x is an element of the reals. Okay? Because if you look at what's happening, right, as the graph continues, this arrow is going up and to the right, right? Now, arrows go in 2 directions most of the time, a vertical direction and a horizontal direction. Okay? When you're considering domain, you've got to look horizontally. So this one is going right, this one's going left. There's an arrow going right infinitely and left infinitely. The domain is anything. X is an element of the real numbers. Okay, so I'm running out of room here, so I'm just going to continue the rest of these down here. So D, the domain is, and there's a couple ways you can write domain. So what you guys have probably seen most of the time is that, yes? Okay, so you also need to be comfortable with this. The domain is the set of x such that x is an element of the real numbers. Okay, that's set builder notation. And then the other type of notation is called interval notation, where you use a set of brackets. And basically, you put the minimum x value on the left and a maximum x value on the right, okay? Now, when x can be anything, the minimum x value is negative infinity, and the maximum x value is positive infinity. So this is going to look like this. It almost looks like an ordered pair. And if the end values are inclusive, meaning you can use the end values as part of the domain, we use square brackets. If they're exclusive, we use curved brackets, okay? Now, infinity is not really a defined value, so whenever infinity is part of this interval notation, you always use these curved brackets. Okay? So that's domain. What about the range? Range is the y values. Yeah,
So I think it would be -4 is the y value, right? Like
the lowest, yes.
so it would be like square bracket -4, and then comma bracket.
Okay, yeah, that's one way, yeah.
It would be y such that y is equal to or greater than -4.
Yeah, so y basically in words, y has to be greater than or equal to -4, because the lowest it goes is -4, goes up from there. Okay, so the range in simplest terms is y is greater than or equal to -4. In set builder notation, the range is the set of y such that y is greater than or equal to -4, comma, y is an element of the real numbers. And then in interval notation, -4 with the square bracket, comma, infinity, round bracket. Okay, because on this end, on the lowest end, -4 is part of the range. On the high end, infinity, we don't have a defined value for infinity, and so we use a curved bracket for that part. Okay, so you have to be comfortable with recognizing all three formats. And then what's the last one? Intercepts. Okay, well, you can kind of see here what the X-intercepts are. What are the X-intercepts? What are the X-intercepts? Yep. 3 and 7, yeah. Y-intercept. Now, can we see the Y-intercept on the graph? No. Okay. What do we know about the X values on the Y-axis? When you're on the Y-axis, what does X equal? 0, yeah. So when you're trying to find a Y-intercept, you can always just plug 0 in for X into the equation, okay? To get the Y-intercept, if you can't see it on the graph, plug in X equals 0, okay? And similarly, if you're trying to get the X-intercept, you can plug in Y equals 0, because everywhere on the X-intercept, or on the X-axis rather, Y is equal to 0, okay? So if we have the function was Y equals X minus 5 squared, so 0 minus 5 squared minus 4. Okay, so that's going to be -5 squared is 25 minus 4, which is 21. That's the Y-intercept. Okay. All right, I think we have time. Is this the last? Yeah, perfect. Okay, so write the equation of a quadratic function that passes through 1, -2, and has a vertex of 3, 2. So here we're trying to find an equation. Okay. Now, you kind of did these types of problems when you were looking for linear equations last year, right? You were trying to find something in the form of y equals mx plus b, and you had certain information about the function, the linear function, okay? Maybe you had the slope, maybe you had a couple points that passed through it, maybe you had the y-intercept. This is a similar type of problem, okay? A place where you can start is, well, what is the vertex form here? The vertex form of all of these is y equals a times x minus p squared plus q. Okay, now, do we know any of these three parameters based on the information that we're given? Do we know any of them? Yeah. We know P and Q, yes. What are P and Q? Yeah, 3 and 2, because we're given the vertex. So this vertex is the point PQ. Okay? So what we're going to do here is fill in what we know. Okay? So the only thing we're looking for here is the value of A. We need to know the value of A. What information have we not used yet? Yeah. Correct. We haven't used the fact that we know a point on this parabola, on this quadratic function. What do you think we could do with this point? Yeah. Sub it in not just for x, for x and y. If we sub 1 in for x and -2 in for y, then we'll only have one unknown, which is A, and we can solve for it. Okay? So we're going to take this and plug in to solve for A. Okay? So y is -2. -2 equals A times 1 minus 3 squared plus 2. Okay, so that's -2 equals A times, this is going to be -2 squared. Right? If you want to take an extra step, you can. Some people can do like going from here down to the next line in your head. That's fine. Okay, so this is -2 equals A times 4. -2 squared is 4, plus 2. Right, and then like subtract 2 from both sides. So we have -4 on the left equals A times 4 is 4A. So what does A equal? Yep. Yeah. Okay, so once you get the A value, don't forget to write out the entire function, because you're asked for the equation of the parabola, right? So the entire parabola is y equals -1 times, what was the vertex again? X minus 3 squared plus 2. Okay, so that's it for today. Tomorrow's class will be shorter because we started some of it today already. I'm going to turn off this recording.